Okay, good afternoon. I'm Yang from ScaleFlux. Today I'm going to present our solution on the computational storage and how to apply it to make the relational database efficiently supported analytical workload. Okay. First is this is marketing stuff. Okay. First, when we are talking about compute, as the Moore's law stops, it's not just the CPU. It's including the FPGA, GPU, and TPUs. Okay. The next innovation comes from the networking. Today, the networking bandwidth increased dramatically. It's very fast. It's already today we can see a 400 GE network. So in that case, people introduced the smart NIC instead of normal NIC to sustain such a high bandwidth of networking. Okay, and then we have this storage, right? We introduced the computational storage, where we move the compute near to the data to make it more efficient. Altogether, we call them as a domain-specific computational solution. They are not just concepts today. Actually, they are already supported by many applications and already in product. We already start shipping products, computational storage products, and see the revenue growth. Okay. So then, why do we want to move compute near to the data? I think you guys already learned quite a lot about that from the previous presentations, but I still want to repeat some of the key points. First of all, it's very effective. Okay, we are not going to offload all kinds of functions from CPU, but there are some functions that can run in much efficient in the hardware instead of just on the CPU side. For example, the compression, the encryption, decryption, machine learning functions, right? By offloading these kind of functions into the hardware, we can make the CPU free many CPU cycles to do whatever the CPU is good at, right? Secondly, we can reduce the I/O traffic. Then you don't need to move this data around the servers to make the I/O efficient. Another very important thing is that we can scale the performance with the workload capacity. Right? So you add more and more capacities, then the performance scales instead of just stuck there. Finally, for sure, everybody claims that we can reduce the TCO. Okay. And there are a lot of more things. If you are interested, you can just ask our marketing guy. So now we like to introduce our architecture about how to accelerate the database workload. Right? The first one is the inline compression and decompression within the storage controllers. Not surprisingly, compression is one of the most popular features in many applications, especially for the database. Generally, it might be okay. You lost some of the user data, but for the database user, it's not acceptable. You have to guarantee all the data are secure. So in that case, in the cloud vendors, they usually save each user data in 3 locations and 3 copies per location, which means one user data has 9 copies within the data center. That's huge. That's a lot of data, right? So in general, you have to enable the compression to save the cost. Unfortunately, it's not that easy. The compression is not always enabled because of the performance penalty. Right? In this case, we offload the compression and decompression built into the flash controller, so it's kind of transparent to the upper layer applications. So you don't see any penalty here. Okay. Besides of the cost saving, first of all, we save these CPU cycles. We offload the CPU, so CPU can do other things instead of just compressed data. Keep busy doing that, right? Second, we can squeeze more bandwidth out of the flash memory because the data transmit between the flash and the controller is much less than before. So essentially, we can get more IOPS than the uncompressed data. Okay. So move one more step forward. Yes.
Quick question on the previous slide.
Mm-hmm.
Where do you capture the transmission from one replica to another replica in this model?
Oh, in this case, we don't do the detube yet. It's just the compression. So we compress data in the block size, like a 4K, 8K, 32K or something.
But if you push the compression into the SSD,
Mm-hmm.
right, or the storage layer, then you don't have another copy of or you don't have a copy of the compressed stream to send across the wire for the other 8 replicas.
Yes. So you mean to do the detube or something?
No, not
No.
to dedupe,
Mm-hmm.
just for the replication, the
Mm-hmm.
cloud case that you articulated.
Yeah, we just say on this, you see the fixed length of the data, you will trunk it in the fixed size of the trunk, right? And then you compress it. Yeah, so
the
what's
point that if the data were compressed on the host CPU,
Yes.
then you could leverage that compression in making copies of the data that is already compressed.
Oh, that's the very
And
good.
that's a bandwidth issue.
So you mean the search window, right? So then you can keep that compressed state to use that data as a dictionary to further compress other blocks. No.
No. You have the computational system
Yes.
that has to perform the write,
Mm-hmm.
right? He's performing the write to his local SSD for a moment, and then that same write has to be done on 8 other locations, if I take your cloud example,
Mm-hmm.
right? Now, if you push the compression into the SSD,
Yes.
then you don't have the byte stream that needs to, the compressed byte stream available to you to send to for the other transmissions.
Yeah.
Now you have increased the bandwidth
Yeah, that's
for
right.
each of
That's
the
right.
other places, which
That-
I would think is a more.
Yeah, I got your point. So some of customers, like what you said, they have some this computational node, and they also have the storage node, and they compress data on the computational node to save the networking bandwidth, right? So in that case, in this model doesn't work in that well because we can only save the bandwidth within this controller, right? So in that case, we already have another solution, which is is still in production with our product. We call it offload model. We just offload the compression with the controller, so you can use the controller as a purely offload engine. So we already have that product, right? This is kind of different envelope. It's kind of transparent to the upper layer application, the upper layer, so it won't worry about all this compression thing. Does that answer your question? So in that case, you can say put the offload engine on that server, right? To compress. It's just purely offload the CPU cycles.
Just a compression engine. then.
Yes, that's right.
So what you're doing is to the compression engine, you're giving it the uncompressed byte stream, getting the
Get the compressed byte stream out of the
and
controller.
then sending that to both your flash.
Yes,
as well
that's
as-
right. That's right. Yes. That's two different models, right? This is kind of an advanced model. It's transparent, but it doesn't mean we use it everywhere, right? For sure. So actually, we see in a customer, sometimes they like this because they don't need to worry about it at all.
The question I would ask is that you talk about improving bandwidth, right?
Mhm.
By doing compression here.
Mhm.
But which bandwidth did you really attack? You attacked the bandwidth between the controller and the flash.
Yes.
You did not attack the bandwidth between the host system and the.
That's right. That's right.
device.
Yes, yeah, it's exactly the same. The bandwidth here is the same as before.
But but that bandwidth is probably your bigger constraint than the other bandwidth.
Yeah, it depends, right? So here, the non-flash bandwidth, for example, we are using a 16-channel controller, so it's provide really high bandwidth on this interface, which is much higher than this one. So you can say, hey, why don't we just, we cannot attack this PCIe bandwidth with this model. But think about it. Today, the NAND is not just constrained by the purely bandwidth. It's constrained by the tprog and the program time and the read time from the NAND. It's kind of latency things. So we attack the bandwidth here, so we reduce the latency from the NAND. So in this case, that's why I didn't present, say, I include this throughput here. Here we just mention about IOPS. So which means we can read and write more data, for 4K block size of data into the NAND more frequently instead of higher bandwidth.
You should also increase the over-provisioning and lower the wear.
That's another thing.
Because you're writing less data.
Yes. So you read the write amplification, and with higher compression ratio, you also reduce the read amplification.
Compared to not doing compression at all.
Yes.
So I think it should be made clear that the left-hand side and the right-hand side are alternative advantages. You're not getting both of them. Left-hand side is compared to when there is no compression at all. The right-hand side is when there is some compression on the host side CPU, and then your question comes.
Yeah, I mean, in general, right, you're better off doing compression on the host side, in my experience.
Yes.
And because that benefits both the wire traffic as well as the disk space and all the benefits that you argue on the storage. I agree, they all exist from wear level and amount of space used. But from a bandwidth perspective, you almost always win by doing compression on the host side.
Right, but then you require devices that will accept a variable size block. So
Yes.
Not disagree.
No, I actually, our customer love this feature because maybe it's more flexible to do compression on host side, but actually it costs a lot of CPU cycles, right? So they don't want to worry about this at all. They just want to say, how about give me the drive that costs less and give me more performance.
So like an FPGA is quite an expensive piece of silicon.
Oh, that's a very good point. Yeah, so I will talk. I will,
other users than just.
that's right. I'm going to talk about it later. But not for now, I can tell you this is not an expensive FPGA at all. It is a very middle range FPGA, and it's very affordable for the commodity SSD. Even for
If you take the same functionality into just raw silicon, it will cost 1/5. We all know that. FPGAs cannot be cheaper than.
Oh yeah, for sure. But we are making system, not just a controller. So that's the thing. Yeah.
So since all the compression is performed inside the SD, right?
Yes.
So how to decide the logical capacity that can be accessed by the users?
Oh yeah, that's
that
it.
depends on the implication of the compression ratio, right?
Yeah, that depends on the compression ratio, right? So generally we expose, we talk to our customer and say, can you estimate your compression ratio roughly? And then we can expose, like say, 4 terabyte raw device, and we can expose say 8 terabyte or even 16 terabyte, right? And also almost all the customers, they have their utilities monitor the usage of the disk, right? And we provide the API for them to call that and to closely monitor the disk, so to make sure it won't run out of space.
So is it possible that you want to store something on the disk, but it should fail because there's no space there?
You mean the backup?
No, I mean, for example, because the logical address that can be used by the users depends on the information, right?
Yes.
But that is decided in advance. But in real system, maybe that it can change a little bit. So sometimes, for example, the exposed capacity is 8 terabytes, right?
Yes.
But when you write already written, for example, 7 terabytes, and then you want to write another block into the disk, but there is no space there.
Yeah, that's why this happens for all the kind of disk. But here we assume the customer can closely monitor the usage of the disk. So generally we set up the threshold. For example, you write so at 90% of the drive, you just stop writing it. Okay, this is another model to move one step forward for the database workload. Right? In general, database just take the data out of the flash and do the decompression and do some data processing on the host side. Right here, we can put both of the decompression and data filtering into the storage, computational storage, right? So to make it more efficient, you can think about it that only a small portion of the data need to be transferred out of the PCIe NVMe interface. Then the CPU won't see that many I/O traffics on it. Okay, so I will take an example how to accelerate these analytical workloads. Right. Before I start, I like to introduce this database workload, OLTP and OLAP. In general, database has two kinds of workload. First one is OLTP, which is transactional processing. It's just like you, for example, you place the order in Amazon, and then Amazon just upload one of the entry in their huge database, right? Another one is the OLAP. AP is analytical processing, which means, for example, if you want to pull the sales report for the past 6 months, so you go through your database and extract this information and analyze it. Ideally, you want to run both kinds of workload on the same database. But unfortunately, it's just impossible. Why? Because the OLAP will touch all the data, scan the whole table through your disk, and that kind of pollute your cache and take a lot of CPU utilization and occupy almost 90 or 100% of I/O bandwidth. So it just makes your TP cannot run it. So it's kind of non-acceptable for the customer. So the database industry, they already have some kind of solutions. They, in general, just say, hey, how about I move the data to another database and do AP there through this so-called ETL. They call it extraction, transformation, and load. But the problem is it's just very complicated. Okay, it's not that easy, just copy-paste from A to B. In general, you have to change data format from row-based, you save data in line to the column-based. Okay, and then even worse, you cannot sync up. It's very hard to sync up both databases. It takes time. You copy data from the TP database to AP database. It generally takes hours, days, or even weeks. So when you run the AP query on the AP database, you always run on the old data. So let's look closely to these AP queries. Generally, for the AP queries, you always run to extract the useful information out of database. In general, you run this like this SQL statement is almost the first one for all the queries. They select the columns, like here names, from this table, which some certain conditions like this country equals to USA. Right? Here, in this case, you can see only small portion of data you need from this big table. It's just an example, but in general, you can reduce you only need, say, reduce the data size by 100 or even 1,000 times. Okay. So here we call projection and predication. Projection is just a select column, and the predicate is just select rows for us which meet certain conditions. Fortunately, actually, the industry already have some kind of solution. They call it database pushdown. Pushdown means like they push this projection and the predication or other queries into the storage engine. Here, the storage engine means a software storage engine. It's not hardware yet. Assuming, say, imagine in general, for example, for many distributed database, they have computational servers running on the upfront to process all these kind of queries. They also have the storage servers running on the bottom to serve all these, handle all these storage things, right? They talk to each other with the networking. So it's pretty common. People say, hey, how about we just push down some of the query into the storage engine, storage node to save the network bandwidth, right? So you only extract small portion of data through this networking. So for us, we further enhance this approach to further push down these queries into this storage, computational storage device. Okay. Yeah, well, here we take the MyRocks as the example application. MyRocks consists of MySQL and RocksDB. The MySQL is, everyone knows, is the most popular open source database. Right? And here, RocksDB is a storage engine application, which support very pretty decent high compression ratio. So the MySQL already support this condition pushdown functions. Ignore this engine or index condition because the engine condition pushdown is just to say you push down the filters or the conditions on the normal field. The index condition pushdown means you push down these filters on the index. But the RocksDB doesn't support it yet. So we have to change some 10 to 20 lines of the RocksDB to bypass this condition pushdown functions into this RocksDB and bypass it to the kernel and send it to our hardware. So this is a diagram show our internal hardware. So on the host side, it's just a standard PCIe NVMe bus. On the media side, we have a flash controller, which is just work like any other modern SSD controllers. It can support the any kind of modern NAND, like a TLC, a 3D TLC NAND. In the future, we are going to support QLC NAND as well, right? So here, to answer the question here, we are using IPGA. And this IPGA, the type is KU15P. It's not super expensive FPGAs, right? We see, actually I saw some kind of people, a solution that use the very expensive FPGA to speed up the database. That FPGA costs around $8,000. So to be honest, I don't think it's a reasonable solution because the whole server may just cost $10,000, right? So here, this is a very affordable solution to the SSD drive. It's not that expensive. Okay, and there are two paths within the controller. The first path is just like other commodity SSD. It's the storage path, right? It's to support the normal storage IOs. Right? Another part is the computational path, which includes some processing engines. Here I just draw 4 engines, but it's just it can be any number of it. It can be 2, can be 8. Depends on how many throughput you want to support. Okay, so each engine can support this the push-down conditions, like the projection, which selects some columns from the table, and support the filter conditions, like equal, non-equal, large, all these common conditions. So from the implementation point of view, to support such high bandwidth, we need to have to, instead of like a software style do the for loop, we have to pipeline everything to make sure the data are processed very effectively, okay? And also on the application layer, we support both asynchronous call and synchronous call. In general, we found it's not, for the single node, it's okay. You can just either use synchronous call or asynchronous call, which one is convenient for you. You won't see much difference on the performance. But in the cloud environment, like we mentioned before, you have the computational node, right? Then talk your storage node through the networking. No matter how fast the network it is, it's still slower than your local I/O. So in that case, we recommend you to use asynchronous call to fulfill the queue, the pipeline, to make sure the hardware busy. Okay. And another very important thing here is the error handling. No matter what happened on your computational path, you should never have any impact on the normal storage I/O. That's very, very important to the customers. They cannot tolerate, say, hey, because of somebody, some application doing bad things on the computational, and then your drive crash the system, right? That's not acceptable. So we have to separate. That's why we have to separate the computational path and the storage path. And also, we do a lot of work to make sure you can recover the computational path can recover from the error. That is very important. By the way, to save the cost, right, to all and the power, there is no DDR in our drive. So we have to streaming in the data and process it and send them out streamingly. So in that case, we modify the data format a little bit by adding the critical information like the size. Actually, this is essentially the size of the block on the top of the data block instead of at the bottom of the data block. Yeah, here's the performance. We run this TPC-H on the as the AP benchmark. So here you see with a single drive, right? We are 60% faster than the CPU solution. This comes purely from this more efficient IPG, right? The hardware is more efficient than the CPU. But even more beautiful, if we increase the number of drives, you can see the latency is not increased that fast as the number of drives. But for the software solution, it's not linear anymore. Actually, it's exponential. In general, it just cannot sustain to support that many of drives. It's 8 drives here. And for us, you can put this 8 drive in a single server. You can still get that many of performance. Yeah, so here's that's why this figure clearly shows why it happened that way. Just like we mentioned many times, it saves I/O, it saves CPU cycle. Okay. Then not much. Also, remember we want to demonstrate this to accelerate analytical workload on the transactional database, right? So in this case, we run a OLTP workload on the front, and on the background, we gradually increase the workload for the AP queries. So in this case, you see, if you take this as a baseline, right? So for the OLTP, you get 100. You say this many of TPS. But if you increase the number of AP workload on the background, the performance drops from 100% down to around only 22%. Okay, with this computational storage, it's only dropped around 10%. But actually, it's not at the end of the story. Okay, so actually in this line, with only 4 threads, which means 4 CPU cores, this SSD already reached the maximum bandwidth for the AP. So it's the performance is already saturated at this point. Okay, but for this CPU solution, you need 32 cores to saturate the AP performance, which means you need another 28 cores to get exactly the same performance as AP solution, as this our hardware push-down solution. So, but even that, the TP's performance sucks. So, which means no matter how many cores you are adding to this to your system, you cannot just simply compensate the gaps between this push-down without this hardware push-down or with the hardware push-down. Okay. Okay, so in summary, the computational storage is already in production, right? We are seeing we are already start shipping the product, and we're seeing the demand in the industry. Also, we demonstrate its value on this database, right? And finally, we optimize the application, the driver, and the hardware to make it working, get the best performance, right? So it's not a big problem for the hyperscale customers. They can optimize everything from top down to the bottom. They have hundreds of engineers working on that. They can squeeze anything valuable for them with no matter what the cost. That's okay. But however, for the whole industry, we want we need the standard to meet that, to make the computational storage fly. So we like to contribute our ideas and share our experience and make it happen. Okay, that's it. Any question? Yeah.
What happens to reliability, data reliability, bit error rates? Any statements on this? Because FPGAs are very prone to single event upsets unless you do certain provision in the FPGA and outside. You lose on bit error rate. Any statements?
Yeah, that's the question is how about the reliability of FPGA, right? Actually, first of all, the software error you were talking some. It happens not just FPGA, it happens on even the ASIC, any silicons, they have similar error. Secondly, that's fact. We are using this Xilinx FPGA, so they provide this ICU solution. They call the background keep tracking the health of the chip. If they found any single bit error, it raises the warning flag. If I found a 2-bit uncorrectable error, it just we just put the drive into a read-only mode to make sure it works. Yeah.
So is the basic way of doing application level RAID or equivalent of RAID basically through mirroring at this point? Because you cannot do RAID 5 or RAID 6 for your data, because you will have device failures and you no longer have all the complete block of data, if you will, for the purposes of doing push-down filtering and projection.
Yeah, first of all, internally we already implement the RAID. It's
internal RAID doesn't count.
If
devices fail.
In that case, remember I mentioned that they have 3 copies per node.
So they count. That's what I'm saying.
Yeah, they count down the other node.
Basically, from my perspective, mirroring. That's the only mechanism of
mirroring. Yes, that's right.
In terms of data formats you can work with besides MyROX, what else?
For now we only support MyROX, but I didn't see the problems to support other kind of storage engines like InnoDB or whatever DB is.
There is a challenge there because MyROX is writing in large extent.
Yeah, that's right.
So you can run, give it a range of block addresses and run filtering function on that. Yes. Whereas the ones that just spray their blocks all over the place. But, it requires a more complex interface to point the drive to sort of stitch together those random blocks.
Yeah, kind of agree with you. For the MyRox, it's kind of hardware friendly in this case because you can go through the continuous blocks. It's a log structure merge tree, so you can just feed data in the streaming style. But we internally, even we don't have DDR, we still have some buffers, and you can just cherry pick some of the blocks for the other kind of database function like B tree structure. You have to cherry pick these blocks and put it into the buffer so you can fulfill the pipeline. In that case, you need relatively larger buffer to compensate the gap. I think it's challenging. Yes, that's right. But even here, we don't. The request is not that much. It's not like 100 megabyte. It's just 128 kilobyte or something. It's already large enough to sustain the throughput. Anything else?
If nobody else is going to ask a question, then I'll ask one.
Sure.
What happens if the disk or the computational storage device is in the middle of one process and then it gets interrupted with some other request? For example, it's doing compression.
Yes.
And the host system says, now store this.
Oh, yeah. Actually, we see even worse scenario like a customer killed the application. And then, and then in that case, we have some callback to sense that event happened, and we just stopped whatever we are doing. Actually, it's kind of normal error handling. If we want to write something out, we just stop writing. But if we want to take something back, we just make up some a dummy date to the full pipeline. And once everything goes through, and we tag the error bit, say this is failed, and then our driver will come back to reset the path, to recover it from the error state. Okay, so that's it.
Thank you.
Thank you.